Hello everyone, today we're going to continue our look at max and min problems, starting with question number 8. So we have a triangle with two sides A and B. The angle between the two sides is theta, and we need to determine the value of theta that maximizes the triangle's area. So this is the situation. We've got a length B, a length A, separated by an angle theta. I've went ahead and called the other side length C. And it may be helpful to look at a few snapshots as we sweep theta to larger values. So if we sweep it to 90 degrees, it looks like this, and Pythagoras' theorem applies here. If we sweep it past 90 degrees, the triangle will look something like this. And notice C is getting larger all the while. So a constraint on angle theta, as I've drawn it in these diagrams, it needs to be between 0 and 180 degrees. If it is equal to 0 exactly, it will be a line of length B because A will drop and they will coincide and it'll be of length B. And if we sweep theta up to and equal to 180, this line will be straight. It'll be collinear with B, and we'll have a line, not a triangle, of length AB, A plus B rather. So something else we can notice, A and B are fixed. They are constant. Theta changes. Theta is the thing we are manipulating, and C responds to that. So theta and C are related, and they are variable. We need to maximize the triangle's area. So we can start by writing the area of a triangle. Base times height divided by 2. We know the base. It would just be of length B. The height, however, is not in terms of A yet. We can do that, and we can do that by maybe making a right angle out of this. So at the top of A, we can just drop a perpendicular line, and that'll be H. In this middle scenario, if we have theta equal to 90, then the height will just be equal to A, and if we push it past 90, if we drop a perpendicular here, it'll be a height given by that. So the height for these triangles, that's a right angle triangle. The height will be hypotenuse times sine of theta. So it'll be A times sine theta. If I were to sub H in for this formula, I would get B times A sine theta divided by 2. So this is the quantity I want to maximize. B and A are both constant. I have an equation entirely in terms of one variable, theta. So all that we need to do now is take the first derivative of this with respect to theta and set it equal to 0 and figure out where the critical values are. So let's do that. So dA d theta is going to be BA over 2 times the derivative of sine theta, which is cos theta. And next we should set this equal to 0. So 0 equals BA over 2 cos theta. And cos theta basically equals 0 when theta equals pi over 2, thinking back to our unit circle, right? So when theta equals pi over 2, that should be our maximum area triangle. So what we should do to confirm that is take the second derivative and double check that the concavity is right so that this is indeed a maximum. I'll maybe leave that up to you to confirm, but pi over 2 is it. So it's basically going to be this triangle here where this angle is 90 degrees. On to the next question. Number 9, we need to determine the maximum perimeter of a right triangle with a hypotenuse of 20 centimeters. So here's the situation. We've got a hypotenuse of 20 that's fixed, and we've got two side lengths here, A and B, that are variable. So this angle theta, imagine, is going to be increasing from maybe 90 degrees to 180 degrees. So if it's at 90 degrees, it's going to be just a straight up and down line. There will be no A and B. So theta should be between 90 and 180 degrees. That's some helpful information. It may be also helpful to look at a few snapshots here. So if we increase theta, and this hypotenuse is sort of falling, so you could imagine maybe that this is like a board and you're letting it kind of fall to the ground. So as it falls further, we have a situation where A and B are equal, roughly. And if we go a little bit further, we now have a situation where B is a little bit longer than A. So we need to maximize the perimeter. So we need to maximize the perimeter. The perimeter is equal to a plus b plus 20. Now we need to take the derivative of this, but unfortunately we have two variables. Now because this is a right angle triangle throughout, a and b are related using Pythagoras' theorem. So we can express either a or b in terms of b or a. We'll maybe switch it so that b is expressed in terms of a, so we could swap out b with a 400 minus a squared rooted. So everywhere I see a b in this equation, I can swap it out with this quantity. So let's do that. P equals a plus root 400 minus a squared rooted plus 20. And now we can take the derivative of this with respect to the only variable that's on the right side, a. So the derivative of a with respect to a is 1. The derivative of this middle term will be 1/2 400 minus a squared to the minus 1/2 times negative 2a using the chain rule. And the derivative of 20 with respect to a is just 0. So let's simplify this a little bit. These 2's would cancel out. We would have a subtraction symbol. I'd have an a up top, and this would be a root in the bottom, 400 minus a squared rooted. Now if we want to determine the maximum, we need to set this to 0 and solve for a. So what we can do is maybe bring this to the left side. So we have a over 400 minus a squared rooted equals 1. Then we can square both sides, giving us a squared equals 1 over 400 minus a squared. Multiply both sides by this, so we would get a squared equals 400 minus a squared. And then bring this a over here, so add a to both sides, we get 2a squared equals 400. Then divide both sides by 2, giving us a squared equals 200. And now a equals root 200. That is the dimension of a that makes the perimeter a maximum. And b is related from before. B is equal to 400 minus a squared rooted, and a is root 200. So if I sub in a root 200 here and square it, that's going to give me 200. And then I root the whole thing. 400 minus 200 is 200, so it'd be root 200. So we found out that a and b will be of equal length, which is approximately 14.14 centimeters. So we've basically solved the situation where it's a 45, 45, 90 triangle. Alternatively, what we could have done with this question is vary theta. So we could have written a as 20 sine theta. We could have written b as 20 cos theta. And then the perimeter would be 20 sine theta plus 20 cos theta plus 20. And then we could take the derivative of this with respect to theta. And eventually we would get a critical number at pi over 4, which is the 45-degree case. And it agrees completely with the solution that we got here using Pythagoras' theorem. For question number 10, we need to determine the dimensions of the rectangle of maximum area that can be inscribed in a circle of radius a centimeters. So there's a couple of ways that we can do this problem. I've kind of gone with the approach that I look at a quarter circle and solve for x and y this way, and it works for this question, but I just need to keep in mind that my actual width will be twice this dimension and my actual height will be twice this dimension. I need to constrain the rectangle to this circle. So this point needs to lie on this circle, which is described by x squared plus y squared equals a squared. And we can do like that and like that, or what we can do instead is use theta. So rather than focusing on the xy coordinates, what we can do is just focus on theta and keep this length at a. So the dimension x is going to be described by a cos theta, and the dimension y is going to be described by a sine theta. So the area then of the rectangle, of the quarter rectangle, will be given by a cos theta times a sine theta. So we can simplify this a bit by saying a squared cos theta sine theta. And because a is fixed, all I need to do with this equation is take the derivative of capital A with respect to theta and see if I can get a critical value out of that. So let's do that. dA d theta is going to be a squared, that's a constant. And then I need to do product rule with this. So it's going to be negative sine theta plus cos theta cos theta. Now I can use an identity with this, knowing that cos x plus y equals cos x cos y minus sine x sine y. So I can simplify this a little bit to be cos of 2 theta. Now dA d theta is equal to that, and I need to set dA d theta to 0 to figure out where my maximum should be. So set that equal to 0, and if I get rid of this a squared, I need to come up with a situation where cos of 2 theta equals 0. Now this equation is true when the argument is pi over 2. So when argument equals pi over 2, this equation is true. So I need 2 theta to be equal to pi over 2, and if I solve further for theta, I get pi over 4. So that's my critical value for theta. And pi over 4 is going to have a situation where x is equal to y, so that's a square. And now I know that x is going to be equal to a cos at pi over 4. And cos at pi over 4 is root 2 over 2. So it's going to be a root 2 over 2. So because the width is going to be twice x, so width equals 2x, the width is then going to be just a root 2. And I know intuitively that at pi over 4, y is going to be equal to x. So that means that y is equal to a root 2 as well. So that's the way I chose to do this problem. I'll just show you briefly another way to do it. So if you do for the full circle, you have the rectangle inscribed here, described by width and height. This full diagonal will be 2a for any w and h that you pick, because h and w are constrained to the circle. So what we can do then, so notice this is a right angle triangle, and the width and the height are related to 2a by Pythagoras' theorem. So what we can do is w squared plus h squared equals 2a squared. And also the area of the rectangle, because we're doing the full rectangle, is just going to be width by height. And now what we can do is figure out width and height. So a is constant. What I should do is express either the width in terms of h or the height in terms of w. So what we can do is express h in terms of w, which is going to be 4a squared minus w squared rooted. And we'd take the derivative of this with respect to w. We would eventually get something, and if you solve for w, you'll get w equals root 2a. So w, the critical value, is going to be root 2a, which agrees with the solution that we did just a moment ago. So question number 11 is going to be for you today. I'll give you a few hints before we move on, but the good news is that the answer is a little more interesting itself than the answers we've come up with so far, because all we've come up with so far is a square and two 45, 45, 90 triangles. So here are your hints. We know this is the situation. This length is 5 centimeters, this is 5, and this is 5. We have the base is 5, and this is the other dimension that we'll need to find the area. And we have a height that will be necessary as well. So it's a bit like the science fair posters where you're displaying your project. These are being sort of folded in or out, so you can see It's a bit like that. So these sort of wings are being moved in and out, and this area inside is changing as a result. So in order for us to do this question, we'll need to know the area of a trapezoid. It's given by this. So we already have the base. We just sub in b there, and we can come up with an expression for a. It may be helpful for you to think of this right angle triangle in here. So this is theta, this is h, this is 5. We can come up with an expression for h here using theta. And similarly, we can swap in a. So we can come up with an expression for a using this right angle triangle over here, and maybe this right angle triangle over here. And we know this length is 5. So we can do our best to rewrite this equation in terms of one variable, theta. This identity may come in handy as well, maybe not. And last, this may also come in handy for you as well. So I'll leave that with you. So this last question of the day may require a little bit more thought than the others we've covered so far. And the difficulty is that it sounds like such a simple question that it may be a little bit difficult to know what to narrow in on. So conceptually, it's a little bit challenging. The math is normal though. Like once you get the setup correct, the math is fairly straightforward to do. So at this moment, I would probably recommend you get a length of spaghetti from your cupboard and the narrowest glass you can muster from your house. And what you're going to do is you're going to model this problem. So here will be your glass. You'll have a length of spaghetti here, and just maybe bring it that way. So see what happens with the spaghetti when you push it that way. And you can also maybe put your hand over top. So maybe put your hand right up against the top of the spaghetti here and see the limitation to navigate the spaghetti out of the glass, and you'll have a little bit more sense of what's going on with this question. So with this question, if you look at the diagram I've drawn here, you need to be able to basically bring this that way, but in order for you to bring it that way, you need this to be able to move a little bit that way, because otherwise it's just going to snap, right? So this end needs to be going away from this wall, which means that it needs to sort of slide forward at that point, and that's going to allow you to rotate it some. So something to notice here, and this is the sort of the crux of the problem, is we can call these angles theta. These are both right angles. I'm going to call this length of ladder from here to there A, and I'm going to call this length of ladder B. So the full length of the ladder would be given by A plus B. And I need to maximize this angle theta, and then once I maximize this angle theta, it'll give me a corresponding length for the ladder. So length A, will be given by, it's the hypotenuse. We have the opposite, which is 4. So if we're using hypotenuse and opposite, we're going to need sine. So sine of theta equals opposite over hypotenuse, A. So it's going to be, if we solve for A, it's going to be 4 over sine theta. And then length B, we have the adjacent, 8, and we need the hypotenuse. So adjacent and hypotenuse, we're going to need cosine. So that's going to be adjacent 8 over B. So that means that B is going to be given by 8 over cos theta. And that's the full thing. So we now have length A given by something in terms of theta, and we have length B given by something also in terms of theta. So we can sub those in for A and B here, and then take the derivative with respect to theta. So I'm going to write A as a cosec, so it's going to be 4 cosec theta, and B I'm going to write as sec, so it's going to be 8 sec theta, and now this is L, so now I can do dL d theta of this. So the derivative of cosec is negative cosec theta cotan theta, and the derivative of sec is sec theta tan theta. So next I'll set the derivative equal to 0, and I would get negative 4 cosec theta cotan theta plus 8 sec theta tan theta. And now I'm going to maybe bring this to the left side, so I'll get 4 cosec theta cotan theta equals 8 sec theta tan theta. So maybe next I'll express these as just a sine and a regular tan, so I'll go 4 over sine theta tan theta equals 8 over cos theta times tan theta. Now what I'm going to do is multiply both sides by sine theta tan theta, so I'll get now 4 equals 8, so this sine would go, we'll maybe put it there, so sine theta over cos theta, and the tan I'll just pair up with that one, so it'd be tan squared theta. And notice sine theta over cos theta is the definition of tan, so I would have next 4 equals 8 tan cubed theta. Now I can divide both sides by 8, so I would then have 1/2 equals tan cubed theta, and I can cube root both sides, so cube root 1/2 equals tan theta, which I can maybe simplify to be tan theta equals 1 over cube root 2. Now, in order for me to get an exact answer for theta, I can use the definition for tan, which is opposite over adjacent, so it's y over x. So basically y is equal to 1, and x is equal to cube root 2. Alright, and then we can use Pythagoras theorem, so we can go r squared equals x squared plus y squared. And let's figure out what r is. X squared will be cube root 2 squared, y squared will just be 1, and then that means that r will be square root 2 to the 2/3 plus 1, so that's r. And we're going to go, because we need to figure out the length L, we're going to sub this in up here, wherever L is, all the way up here, 4 cosec theta, 8 sec theta. So I've found the critical value for theta, and it needs to be consistent with these values for y and x and r. So I can sub y and x and r into this to get an exact value for L. So let's maybe do that now. So L is equal to 4 cosec. So cosec is 1 over sine. So sine is opposite over hypotenuse, so cosec would be hypotenuse over opposite. So hypotenuse is r, which we found to be 2 to the 2/3 plus 1 rooted. Okay, and then we divide by the opposite, which is the y, which is 1. And then we add 8 sec, so it's going to be 8, and then hypotenuse over adjacent. So the hypotenuse is again this one, 2 to the 2/3 plus 1 rooted, and then we divide that by x, which we found was cube root of 2. Now we simplify this a little bit, so what we can do now is maybe take out a 4 and this root 1, so it'll be 2 to the 2/3 plus 1 rooted, and we can also factor out maybe a cube root 2. Now when I distribute this back in, it should give me this expression. So this first one should be cube root 2, right? When I multiply this by that, it gives me this thing. And the next one should be just a 2. And that's the length of the ladder. So we did it, which is approximately equal to 16.6 feet. So it's 16.64775.274, but that's the length of the ladder max that we can fit. So that's it for today. I'll see you next time.